In this lesson, we're going to learn how to accurately sketch the graph of a function by putting everything together that we've learned about identifying where a function is increasing and decreasing, concave up, concave down, identifying relative extrema and vertical asymptotes, etc. Now down here, we have some guidelines that we're going to follow when we're sketching the graph of a function. So the first thing that we'll want to do is to find where the function is increasing and decreasing. Then we'll want to identify where the function is concave up and concave down. We will find the location of any relative extrema and inflection points. We'll also find any vertical asymptotes, and we'll determine the end behavior of the function, in particular taking note of any horizontal asymptotes. Then we will also want to find any Y-intercepts. Those are usually easy because all it involves is evaluating f of 0. And if possible, identify any X-intercepts. Now sometimes that can be difficult because solving an equation like f of x equaling 0 can sometimes be rather difficult if it's a high degree polynomial. So sometimes we'll skip this step. And then after we have all this information, then we'll just plot the function using everything that we found in steps 1 through 8. Now let's take a look at a few examples. So here we want to sketch the graph of the function 3x to the 4th plus 4x cubed. So, going through our guidelines, we first of all want to find where the function is increasing and decreasing. So we want to find where the first derivative is positive and negative. So we take the derivative, and we find where it is 0 or does not exist. Now of course for this one we don't need to worry about DNE because this is a polynomial. That derivative exists everywhere. So solving this equation for 0, notice we can factor out a 12x here and we get 12x squared we can factor out and we get, and so we get x equals 0 and negative 1. So those are our critical numbers for our function f of x. So now we'll set up our number line and we'll plot 1, 0, and negative 1. Pick test points, negative 2, negative 1/2, 1. Put these numbers into the first derivative. Here's a nice factored form, and identify where our derivative is positive and negative. So we're looking here at the sign of f prime. And so let's see, if we put negative 2 in here for x, this term is always positive. 12x squared is always positive. So if we put negative 2 in here, we get a negative number back. So that's where we are decreasing. And then we are going to be, let's see, if we put negative 1/2 in here for x, this is positive times positive. Negative 1/2 plus 1 is positive, so we're increasing from negative 1 to 0. And then if we put 1 in here for x, we're also positive. So there we go. So that identifies where we are increasing and decreasing. So we are increasing from negative 1 all the way to infinity, and decreasing from negative infinity to negative 1. Let's identify relative extrema. So we have a relative maximum. Well, doesn't look like we have any here, because we don't see a positive to negative change. So we have no relative max, relative min. Well, that's going to be at -1 because we're decreasing and then increasing. So that's going to be at -1, f of -1. And if we put -1 back in here for x, notice we will get 3 minus 4. So -1, -1 is where we have a relative minimum. Now let's identify where the function is concave up and down and identify any inflection points. So concavity. So we need to take the second derivative. So that's going to be set that equal to 0. Now we don't need to worry about dne again because this is a polynomial. So we'll just set it equal to 0. And factoring this if possible, we're going to get, we can factor out a 12x out of there. And so we get x equals 0 and -2/3. Setting 3x plus 2 equal to 0, notice that this will equal 0 if we put 2/3, -2/3, right in there for x. So let's see, now we have to find out where our function is increasing or concave up and concave down. So we will look at the sign of the second derivative. Let's mark off our numbers here on the number line. So we'll mark off 0 and -2/3. Pick some test points like 1, -1/2, and -1. Let's see, if we put -1 into our second derivative here, this will be negative. -1 going in here for x, this will be negative as well. -3 plus 2, that's negative, so we will be positive here, concave up. If we put -1/2 in here for x, this will be negative. This will be a positive number. 3 times -1/2 is -3/2 plus 2. That's going to be positive 1/2. So negative times positive is negative. So we're concave down from -2/3 to 0. And then if we put 1 in here, of course, we'll get back positive. There we go. So we are concave up. From -∞ to -2/3. And from 0 to infinity. And concave down from -2/3 to 0. Let's identify any inflection points. Well, we have a change in concavity across -2/3, and f of 2/3 does exist, as does the derivative at -2/3. So we will have an inflection point there, so that will be at -2/3. And evaluating f of, remember we put this back into the original function, f of -2/3, that will be -16 over 27. And that's approximately -0.6. And we also have an inflection point at 0. See, we have changed from concave down to concave up. 0. And if we put 0 back into original function, we get back 0. 3 times 0 plus 4 times 0. So there are both of our inflection points. Now let's take a look at any end behavior and x and y intercepts. Now, the end behavior for this polynomial, since this is a 4th degree polynomial, we see that the limit as x approaches positive infinity of our function is going to be positive infinity, because this is a 4th degree polynomial with a positive leading coefficient, and also the limit as x approaches negative infinity of f of x is going to be positive infinity as well. Let's just take note of that. Once again, because that's a fourth degree polynomial, which is an even number. Now let's see any y-intercepts. So a y-intercept, if we put 0 in here for x, f of 0 is 0, of course, so 0 is our y-intercept. Any x-intercepts? Well, if we set our function equal to 0, let's see if they're easy to find. So if we set 3x to the fourth, let's note that we'll set this equal to 0. Let's first of all note that it factors as so we see if we set this equal to 0, we see that we have x-intercepts at 0, setting x cubed equal to 0, and negative 4/3. And let's also note that we have no vertical asymptotes here, of course, because this is a polynomial. It's not a rational function, so vertical asymptotes, none. And of course no horizontal asymptotes, because we already looked at our limiting behavior as x approaches infinity and negative infinity. Now let's sketch the graph of this function. So let's plot our relative extrema first. So we have a relative minimum at -1, -1. So let's just plot, let's say there's -1 on the x-axis, -1 on the y-axis. So there we have a relative minimum. Let's plot any inflection points. So we have an inflection point at -2/3, -16/27, which is approximately -0.6. So let's plot that point right about here. And also 0, 0 is another inflection point right there. And I think we're about ready to graph this function. Oh, x and y-intercepts. Let's see, the y-intercept is 0. We already have that plotted right there. X-intercept 0 and -4/3. We already have 0 plotted. -4/3. Let's put that right about there. And that's all the information that we have to go on as far as points go. Now let's see what our increase and decrease in concavity tell us. So from negative infinity up to -1, looking back at the sign of our first derivative and the sign of our second derivative, we see that our function is decreasing and concave up. And we know that as x approaches negative infinity, our function approaches infinity. So our function is going to come down like this, decrease, be concave up. It goes through that point right there. This is a minimum. So it's going to come down, touch that point. Now it's got to go up to this point. Let's see. So from -1 to the x-coordinate of this point was -2/3. So now we have to increase. Notice we're increasing from -1 to 0. And we are, until we hit this point, we are concave up. So concave up. Then we have to go from here to here, so we will continue to increase, but we will be concave down. So we'll try to make it look concave down here like that. And now we're at 0. Now let's see. What we have to do is we have to increase, and we have to become concave up. So now we have to increase and be concave up. And there is a rough sketch of the graph of this function. Let's see how this compares to the actual graph if we were to use a computer to graph it. So here's what the actual graph looks like. And here's the graph of the function, and it looks exactly like what we had graphed. Notice we have a relative minimum right here at -1, -1. Right about here is our inflection point. That was the point -2/3, -16/27. Right here we have another inflection point that was 0, 0. And yeah, it does look like our function was decreasing from -infinity to -1, increasing from 1 to infinity, concave up from -infinity up to -2/3. See, that's where it's concave up. Concave down from -2/3 to 0, and then concave up from 0 to infinity. Now let's take a look at another example. In this example, we want to sketch the graph of the rational function x² divided by x² minus 9. Now we're given the first and second derivatives for this function, and you should verify that you can do these by hand. You just have to use the quotient rule when you're differentiating. Now, the first thing we want to do to graph this function is to find where f of x is increasing and decreasing. So we want to find where the derivative is positive and negative. So to do that, we first find where the derivative is 0 or does not exist. Now, the derivative will equal 0 when the numerator is equal to 0. So setting 18x equal to 0, we get that x equals 0, of course. And the derivative does not exist when the denominator is equal to 0, and that's when x² minus 9 is equal to 0. So x equals plus and minus 3. Notice if we put 3 in for x, we get 0, and -3. We get 0 in the denominator as well. So now we have to find where the derivative is positive and negative, so we'll use our sign pattern technique. And we'll pick some test values like 1, -1, 4, and -4. And notice that if we put -4 into the derivative function, we will get, now keep in mind we have a negative out here, we will get 18 times -4, that's going to be a negative number. This negative will make it positive. Now notice that the denominator is always positive because of this 2 right here, because of the square. So we don't really need to worry about the sign of the denominator. It's always positive. So in the numerator, we're going to get a negative number times a negative number, -4 up here. So that will make it positive. If we put -1 in for x, in the numerator, we'll get a negative number times negative. That'll make it positive as well. So we're still positive here. Now if we put +1 into the derivative function, the numerator will now be positive, but we have that negative out here. Denominator is always positive, so we will be negative in here. And if we put 4 in, same thing. 18 times 4 is positive, but we have that negative out here, so negative. And this is where we are going to be increasing and decreasing. Remember, the pluses and minuses here represent the sign of f prime. So we see that we are increasing from -infinity to -3, and from -3 to 0. Notice I didn't write this as -infinity to 0 because our function up here, as we will see, has a vertical asymptote at -3. Notice if we put -3 in here for x, we get 9 divided by 0. Negative 3 squared is 9 minus 9. That'll be 0. So we're actually going to have a vertical asymptote at negative 3. So we should not say we're increasing across a vertical asymptote. So that's why we left the increasing interval broken up as two separate integrals instead of just saying negative infinity all the way up to 0. And decreasing is the same thing. We're going to go from 0 to 3, and then 3 to infinity. And same reasoning, we don't want to say we're decreasing from 0 to infinity because we have a vertical asymptote at 3. Let's identify any relative extrema. We see that we are increasing and then decreasing at 0, and so that is going to be where we have a relative maximum. Also notice 0, if we plug it into the function f, we do get a number back. It's not, f of x is defined as 0. So we will have a relative maximum at 0. F of 0, now if we put 0 into our function up here, we get back 0, right? So that's where we have a relative maximum. Now let's identify where our function is concave up and down. So the second thing, we need to look at the second derivative now, the sign of the second derivative. Let's notice our second derivative is 0 or does not exist. Let's see, the numerator is never equal to 0, right? X squared plus 3, that is never 0. The denominator, that does equal 0 when x is plus and minus 3 again. So that's where we're going to have critical numbers for f prime, where the second derivative is 0 or does not exist. So that's going to be, so f double prime does not exist at plus and minus 3. And it's not equal to 0 anywhere. We don't have to worry about it equaling 0 because the numerator is never 0. So let's do our sign pattern now for the second derivative, and we'll determine where the original function is concave up and down. And we'll pick some test points like 0 is a nice convenient number, 4 and negative 4. Notice how I try to keep the sign of the first derivative and the sign of the second derivative, the number lines lined up. So that way it makes it a little easier to graph the function. Now if we put negative 4 into the second derivative, you'll notice that the numerator is always positive, right? X squared plus 3, that's always positive. So we don't need to worry about the numerator changing sign. The denominator will change sign. If we put negative 4 in for x, we will get 16 minus 9, that's a positive number, cubed, so that will be positive. And the top is always positive. So we will be concave up from negative infinity to negative 3. If we put 0 into x, the top will be a positive number. The bottom will be negative. We will get negative 9. 0 minus 9, that's negative 9 cubed. Negative 9 cubed is a negative number. A negative number cubed is negative. So our function is concave down from negative 3 to 3. And then if we put positive 4 in here for x, we will get positive divided by positive. 16 minus 9 is positive. So concave up. And there, so now we know where our function is concave up and down. So we have concave up from negative infinity to negative 3, and from 3 to infinity. And we are concave down from negative 3 to 3. There we go. Now let's identify any inflection points we have here. Well, we do see that we have a change in concavity occurring at negative 3. However, as we'll see, at -3 our function is not defined, right? That's actually going to be where we have a vertical asymptote. So -3 does not represent where we have an inflection point because the function is not defined at -3. The same thing at +3. We have a change in concavity, but our function is not defined at 3, so we don't have an inflection point there either. So we have no inflection points. Now let's identify any vertical asymptotes. Well, we see that the denominator here is equal to 0 at plus and minus 3, and at plus and minus 3 the numerator is 9. So we're going to have a vertical asymptote at plus and minus 3. So that's going to be at -3 and x equals +3. Those are the vertical asymptotes. And let's see about any horizontal asymptotes. Well, let's notice that the limit as x approaches infinity by our rules for limits at infinity, the degree of the top is the same as that of the bottom, x squared and x squared. So the limit as we approach positive or negative infinity is going to be the quotient of the leading coefficients, which in this case are 1 and 1. And so this limit is going to be 1. And that's true for negative infinity as well. So we could just write here plus or minus infinity. So we have a horizontal asymptote of y equaling 1. That's our horizontal asymptote. And here are the vertical asymptotes up here. Now let's note any x and y-intercepts. Well, our y-intercept, that's easy enough to find. If we put 0 in here for x, f of 0 will be 0 divided by -9, so that is 0. So that's where we're crossing the y-axis. And any x-intercepts, well, that we would obtain by setting the numerator equal to 0. So we would set x squared equal to 0. Well, of course, we get back 0 there. So those are the values where we're crossing the x-axis. So it just so happens that our x and y-intercepts are the same. And if you want to, you can write these as coordinate points as well. This would be 0, 0. That's the point on the y-axis. And down here, the same thing, 0, 0. Putting 0 in for y and solving for the x's, well, we just got back 0 for the x. Now we can sketch the graph of this function. So let's notice all of our information up here. We've got a relative maximum at 0, 0. Let's plot that right here. We have vertical asymptotes at plus and minus 3. Let's sketch those. So let's say 1, 2, -3, 1, 2, -3. So we have vertical asymptotes occurring here and here. So that's at 3 and -3. We have a horizontal asymptote of y equals 1, so let's put that in here, right here. So there's a horizontal asymptote. Now we can start sketching the graph of our function. Oh, notice the x and y-intercepts are 0, 0, and we already have that point there. That's actually a relative maximum. So now, let's see. If we go from negative infinity to -3, our function has to be increasing as we get towards -3 and concave up. This is a horizontal asymptote, so it has to hug this line out here, this dotted line, and as we come towards a vertical asymptote here, we're either going to break up or break down. Well, we have to stay increasing and we have to be concave up, so we are going to have to break upward. So that's what the graph of our function is going to look like on that piece. Now, as we go from our vertical asymptote towards this point, we either have to come down like this or come up towards that point. Well, as we go from -3 to 0, -3 to 0 we should be increasing, and -3 to 0 we should be concave down. So the only way we can do that is if our graph goes like this. And now we have a relative maximum right here. Now our graph is either going to have to go up towards the vertical asymptote like that, or down like this. Well, it's a maximum here, so we should break down. Let's also note from the sign of f prime, we see that we should be decreasing and concave down. So we have to go like this, break down towards negative infinity at this vertical asymptote here. Now as we go from 3 to infinity, we should be decreasing and concave up. Well, the only way we're going to be decreasing from this vertical asymptote is if we come down from positive infinity, and then we have to hug that line. So we have to come down, remain concave up, and then start getting close to that dotted line. And there, that's what the graph of our function looks like. Let's take note of the graph that we have from graphing it on a computer graphing system and see if it matches up with this information that we have here. And so here's what our graph looks like by graphing it on a computer graphing system. Notice that right here we have our vertical asymptotes at -3 and +3. We have a horizontal asymptote at 1. We have a relative maximum right there at 0, 0, and that's also our X and Y intercepts. And notice how our graph hugs the dotted line, increases to infinity as we approach the vertical asymptote. Then we jump over the vertical asymptote, come up from negative infinity, approach 0, 0, drop back down, and then crossing over this vertical asymptote, we come down from infinity and remain concave up as we go towards positive infinity and hug the horizontal asymptote. So this looks exactly like what we had graphed. So that verifies what we did. In this example, we want to sketch the graph of the rational function x² - 1 over x² + 1. Now, we're given what the first and second derivatives are here for this function. You should verify these derivatives by hand using the quotient rule to differentiate f and differentiating f prime to get f double prime. Now, to sketch the graph, we first have to find where the function is increasing and decreasing. So we have to find where the first derivative is positive and negative. So to do that, we need to find where it's equal to 0 or it does not exist. Now it's going to equal 0 when the numerator is equal to 0. So that's when x is equal to 0. And this derivative exists everywhere. The denominator x² + 1 is never equal to 0 anywhere, so we don't have to worry about dividing by 0. So this is the only critical number we have for the function f, so we'll set up our sign pattern for the first derivative. And just pick some simple test values like -1 and 1. Putting these two test values into our derivative here, if we put -1 in for x, we see that we're going to get a negative number divided by a positive number. Notice that the denominator is always positive because of the square right here. So we don't have to worry about that. It's the numerator that's going to determine the sign of f prime. So putting -1 in here, we get a negative number back. Putting +1 in for x, we get a positive number back. So there, that's where we are increasing and decreasing. So we're increasing from 0 to infinity, and decreasing from negative infinity to 0. And we have a relative minimum at 0. Our function is decreasing and then increasing. So that's where our relative minimum is occurring. And if we put 0 into our original function here, we get back -1. So that's the location of our relative minimum for this function. Now let's find where our function is concave up and down. So we have to set our second derivative equal to 0, or dne. So the second derivative will equal 0 when the numerator is equal to 0. So setting 3x squared minus 1 equal to 0, notice the -4 doesn't really do anything, that just cancels with the 0 on the other side. This will imply that x equals plus and minus 1 divided by the square root of 3. Just take the 1 over to the other side, divide by 3, and then take the square root of both sides. Notice you do need a plus or minus when you take the square root of both sides. So we have that. Those are critical numbers for the first derivative. And where does the second derivative not exist? Well, the second derivative exists everywhere because the denominator is never equal to 0. Right? X squared plus 1, that is never equal to 0. So we don't have to worry about dividing by 0. So the second derivative exists everywhere. So this is not coming into play. So let's set up our sign pattern now for the second derivative. And marking off plus and minus 1 over root 3. Now, 1 over root 3 is approximately 0.58 and -0.58. So we'll pick some test values like 0, -1, +1. Put these values back into the second derivative up here and see if we get back positive and negative numbers. See what our sign is. So if we put -1 in here for x, we're going to get -4 times 3 minus 1. So that's a positive number. -4 times a positive number, that will be negative. So our function is concave down from negative infinity to -1 over root 3. If we put 0 in for x up here, we're going to get -4 times -1 in the numerator. Notice the denominator is always positive because of the x squared plus 1. That's always positive. So putting 0 in here, we get -4 times -1. That is positive. And then putting 1 in for x up here, we get -4 times 3 minus 1. So that's going to be negative in the numerator. Denominator is always positive, so negative. So we're concave up from -1 over root 3 to +1 over root 3, and concave down from negative infinity to -1 over root 3, and from +1 over root 3 to infinity. And let's identify any inflection points. Well, we have a change in concavity at -1 over root 3. And if we put -1 over root 3 back into the function f of x, check it out, you'll see that you get -1/2 back. So we have inflection points at and once again, just check out that if you put -1 over root 3 in for x up here, you get back -1/2, and also at +1 over root 3. So there are our inflection points. Now let's check out any vertical asymptotes. Well, we don't have any vertical asymptotes because the denominator up here is never 0. X squared plus 1 is never 0, so no vertical asymptotes. Let's check out any horizontal asymptotes. So we have none. No vertical asymptotes. Horizontal asymptotes. Well, the limit as x approaches infinity of this function well, using our rule that states that we can just look at the quotient of the leading coefficients if the degree of the top equals the degree of the bottom, which they do in this case. So this limit is going to be 1 over 1, which of course is 1. And the same thing for negative infinity. Positive, so we'll just put positive or negative infinity here. So we have a horizontal asymptote at y equals 1. So that's where we have a horizontal asymptote. Let's check out any x and y-intercepts. So a y-intercept, if we put 0 in here for x, we get back -1. So the y-intercept is at -1. Let's see if we can find any easy x-intercepts. So if we were to set x squared minus 1 equal to 0, the numerator, well, that gives us back plus and minus 1. So those are the x-intercepts. Now we have enough information to graph this function, so let's try to sketch an accurate graph of it. So let's see, we have x and y-intercepts. The y-intercept is at -1 right there. The x-intercepts are at plus and minus 1, so those points are on the graph. We have a relative minimum at 0, -1. Well, that just happens to be our y-intercept, so there's our relative minimum. We have inflection points at -1 over root 3, -1/2. Now, 1 over root 3, remember, that's approximately 0.58. So we'll mark those right about here. And 1 over root 3, -1/2 is going to be right around here as well. And we have a horizontal asymptote of y equaling 1. So this is our horizontal asymptote. Now, as we go from -infinity up to -1, right, there's -1, our function is decreasing right there, and we have to be hugging this line right here, this dotted line. So our function has to be decreasing to this point, and also note that it is concave down. See over here, we are concave down from -infinity to -1. So our graph is going to go like this. Then we have to pass through this point right here. Alright, now we have to go from here to here. Now let's see, we are going to continue to decrease until we get to 0, right? We're decreasing from -infinity all the way up to 0, right there. And we are still going to be concave downward until we get to this point. Now once we hit this point, we have to get over to this point, so we continue to decrease, but now notice we are going to be concave up from -1/√3 to 0. So now we're concave up. This is a relative minimum right here. Now we have to go from this point to this point, so obviously we have to increase. Well, we're increasing as soon as we pass 0. We're going to be increasing all the way to positive infinity now. And we are also concave up until we get to 1/√3. So we're concave up right here like this. Now we have to go from here to here, and so we have to be increasing, which we are. And once we pass this point, the x-coordinate of that point is 1/√3. Now we have to go concave down. So concave down like that. And then this is a horizontal asymptote, so we will have to then increase, remain concave down, and start approaching that line. And there is a sketch of what the graph of this function looks like. Now let's take a look at a computer-generated graph and see if it matches with what we found here. So right here is what the graph of that function looks like. Notice right here we have a relative minimum, that is the point 0, -1. We have x and y, and x-intercepts at -1 and +1. Now it's a little difficult to see, but right here is our inflection point. That point right there is -1/√3, -1/2. And we have another inflection point right there. That is the point 1/√3, -1/2. And then notice we have a horizontal asymptote of y equals 1, like that. And yes, this is exactly what the graph of what we had previously sketched looks like. So that verifies what we had sketched earlier.